Спасибо. Okay, in the previous lecture we introduced polynormed spaces, that is, vector spaces equipped with families of seminorms. And we observed that every polynormed space has a canonical topology, which makes it into a topological vector space, which means that the algebraic operations, that is, the addition and multiplication by scalars, are continuous. And we gave a number of concrete examples of such spaces, including some spaces of continuous functions, of smooth functions, and of holomorphic functions. An important example is the famous Schwarz space of rapidly decreasing smooth functions on Rn. So the natural question now is whether or not all topological vector spaces arise in this way. And the answer is no. And today our first goal will be to give a geometric characterization of such polynormable spaces within the class of all topological vector spaces. And towards this goal, at the previous lecture we discussed some geometric notions related to convexity. And at the very end of the lecture we introduced the notion of a Minkowski functional. So to begin with, let's recall how this functional is defined. So we start with a vector space, X. Let's recall that all our vector spaces are over the real numbers or over the complex numbers. So this is our base field. And suppose that S is an absorbing subset of X, which means that for every X in X, there is a constant, positive constant, such that X belongs to lambda S whenever lambda is big enough in this sense. So such sets are called absorbing. So the Russian for absorbing is поглощающий. So geometrically, this means that S swallows every point if we inflate it in a suitable way. The Minkowski functional of S is a function, PS, and a negative real-valued function on our space, given by the following formula, which is the infimum of those non-negative lambda, such that X belongs to lambda S. Since S is absorbing, this set is non-empty. So this definition makes sense. The set is non-empty. By the way, let's recall, I will use this observation several times today. Let's recall that every neighborhood of 0 in a topological vector space is absorbing. This easily follows from the continuity of multiplication by scalars. So a typical absorbing set is a neighborhood of 0 in a topological vector space. So this is the Minkowski functional. So to begin with, let's look at some basic properties of the Minkowski functional. So we have the following proposition. First of all, the Minkowski functional is positive homogeneous in the sense that we have the following equality for every non-negative number lambda. Second, I claim that if our set S is convex, then PS is sub-additive, that is, it satisfies the triangle inequality. Next, I claim that if S is circled, circled, then PS is homogeneous in the sense that PS of lambda x is the absolute value of lambda times PS of x for every scalar lambda and for every x. Well, just in case, let me remind you what circled means. So a subset S of vector space X is circled or balanced if it is stable under multiplication by scalars of modulus less than or equal to 1 for every lambda. Satisfying this condition, we have the following inclusion. Geometrically, this means the following if we work over the real numbers. So if this is a point x in S, and this is 0, then such an interval, which is symmetric about 0, is contained in S. So if we work over the real numbers, then such lambda run over the interval from -1 to 1, and such an interval has to be contained in S. And by the way, in this case, the word balanced is more adequate. And if we work over the complex numbers, the geometric meaning is that for every point x in S, the following disk centered at 0 is contained in S. Because in this case, if over the complex numbers, such scalars lambda run over the closed unit disk on the complex plane. And in this case, in the complex case, the word circled looks more relevant. So anyway, we use these words as synonyms. I personally prefer the word circled because I love complex numbers. But anyway, these words usually are used as synonyms for this property. Okay, let's come back to the properties of the Minkowski functional. Property 4 is that if S is absolutely convex, which by definition means that it is convex and circled simultaneously. Then PS is a polynorm. PS is a seminorm, which is in fact immediate from 2 and 3. A seminorm is a function satisfying this property and this property. So PS is a seminorm, and moreover, we have the following inclusion. The open unit ball for PS is contained in S, and the S is contained in the closed unit ball relative to PS. Let's recall the notation here. So if P is a seminorm, on a vector space, then UP is in the following set. So this is the open unit ball for P, and the UP bar is the respective closed unit ball, which is given by the following inequality. Okay, so as for the proof, property 1 is almost immediate from the definition. So this is a simple exercise for you. Property 2, well, let me prove property 2. It's not so immediate. It's almost immediate, but not exactly. So to prove property 2, we do the following. We take any positive epsilon, an arbitrary positive epsilon, and find two non-negative numbers, lambda and mu, such that x belongs to lambda s, y belongs to mu s. Such numbers exist because s is absorbing, and such that lambda is smaller than ps of x plus epsilon, and mu is smaller than ps of y, again plus epsilon. We can always choose lambda and mu in such a way, well, just by the definition of the infimum. Okay, now let's look at x plus y. X plus y then belongs to a lambda s plus mu s. And at this point, I claim that lambda s plus mu s is precisely lambda plus mu times s. This equality is, again, a little exercise for you. It's immediate from the convexity of s. So this property is true by the convexity of s. Okay, now x plus y belongs to the set. We now use the definition of the Minkowski functional and deduce that ps of x plus y is then less than or equal to lambda plus mu. And in turn, lambda plus mu is less than or equal to ps of x plus ps of y plus 2 epsilon. And since epsilon is arbitrary, we obtain the result. Okay. Well, property 3 is again very simple. It's an exercise for you. The first part of statement 4 is immediate from 2 and 3. So PS is a semi-norm. PS is a semi-norm by 2 and 3. Also, the second inclusion, this one, is immediate from the definition of the Minkowski functional, as is contained in the closed unit ball. This is clear. Just look here. So if s is already if x is already an s, then this property holds well in the case where lambda equals 1. So the infimum can be only less than or equal to 1. And this means that we sit in the closed unit ball. So this inclusion is clear by definition. And to show that the open unit ball is contained in S, well, let's take an element in this ball. So this means that ps of x is smaller than 1. So the infimum is less than 1, and so we can find a number lambda such that lambda is also less than 1. There exists a positive number smaller than 1, such that x belongs to lambda s. Well, then this implies that lambda inverse of x belongs to s. And since s is circled, we can multiply it by lambda. S is stable under multiplication by every such number lambda. We deduce that x belongs to s, because s is circled. And this gives us the second inclusion. The open ball is contained in S. Okay, so these are the properties, the basic properties of the Minkowski functional. And now we can give a geometric characterization of polynormable spaces, that is, of those topological vector spaces whose topology can be given by a family of semi-norms. It turns out that the class of such spaces coincides with the class of locally convex spaces. So we have a following definition. We say that a topological vector space X is locally convex if there exists a base of neighborhood of 0 X consisting of convex sets. Let's, by the way, observe that instead of a base, we can replace a base by a subbase. Because, because intersections of convex sets are convex. So if we have a subbase with 0 consisting of convex sets, then by taking finite intersections, we get a base of neighborhoods of 0 consisting of convex sets. And a standard abbreviation, so for brevity, by a locally convex space, we mean a locally convex topological vector space. Locally convex space is the same as locally convex topological vector space. And we abbreviate it as LCS. Actually, we already have a number of typical examples of locally convex spaces because of the following simple observation. Let's observe that if we start with a polynorm space, if XP is a polynorm space, that is a vector space together with a family of seminorms, then the canonical topology generated by P, 2 of P, let's call that this topology consists, the standard subbase of this topology consists of all open balls with arbitrary centers generated by the seminorms from P. So this is a locally convex space. We already know that this is a topological vector space, and I claim that it is locally convex for the simple reason that the respective balls, UP, are convex. And moreover, they are absolutely convex. And such balls, together with their, if we multiply them by arbitrary positive numbers, we get a standard subbase of neighborhoods of 0. So every topological vector space of this form is locally convex. And our first fundamental result in this course is that the converse is also true. So we have the following theorem. A topological vector space X, let's denote the topology of X by 2. A topological vector space is locally convex, even only if its topology is given by a family of seminorms. There is a family P of seminorms of X such that the topology 2 is generated by P. And let's now introduce the respective terminology. Any such family is called a defining family for X. Any such P is a defining family. Okay, so to prove this theorem, we first need a simple lemma. First of all, I claim that if X is a topological vector space, an arbitrary topological vector space, then every neighborhood of 0 contains a circled neighborhood of 0. Each neighborhood of 0 in X contains a circled neighborhood of 0. And statement 2, if moreover X is locally convex, if X is a locally convex space, then each neighborhood of 0, X, contains an absolutely convex neighborhood of 0. That is convex and circled. Absolutely convex neighborhood of 0. Well, let's prove the lemma. So first of all, we take a topological vector space X. We take a neighborhood of 0. Let's denote it by U. Let U be a neighborhood of 0. And let's consider following set D bar. This is a subset of K of our base field given by the following inequality. So if our base field is the field of complex numbers, then this is the closed unit disk centered at 0. And this is the reason why I denote it by D. And in the real case, this is just the interval from -1 to 1. The closed interval from -1 to 1. And let's now take the following set. Let V denote the product of G bar and oh, sorry, not this way exactly. Sorry, just a moment. Okay, so the multiplication by scalars is continuous. The multiplication by scalars is continuous, and so we can always find a neighborhood of 0, V, such that dV is contained in U by the continuity of the multiplication. Formally, if we apply the continuity of this map formally, then there is a neighborhood of 0 here and a neighborhood of 0 here, such that their product is contained in U. But the first neighborhood of 0, which is in K, can always be chosen to be the closed unit disk. In the general case, this is a disk of radius epsilon, but we can make it into a disk of radius 1 if we multiply V by epsilon. So by changing V, we may assume that the first neighborhood, which is in here, is just the closed unit disk. Okay, so there is such a neighborhood, and let's look now at dV and observe that this is nothing but the circled hull of V, that is the smallest circled set containing V. This is a circled neighborhood of 0. A circled neighborhood of 0. And this completes the proof of part 1. It is a circled neighborhood of 0, and it is contained in U. It is a neighborhood of 0 because V is a neighborhood of 0, and this one is bigger than V. So it is also a neighborhood of 0. Okay, part 2. To prove part 2, we may assume from the very beginning that U is convex, because every neighborhood of 0, by definition of a locally convex space, every neighborhood of 0 contains a convex neighborhood of 0. So we may assume that U is convex. And by part 1, there exists a circled neighborhood of 0, W, such that W is contained in U. And to make it absolutely convex, let's just take the convex hull. Let W prime denote the convex hull of W. Then W prime is absolutely convex neighborhood of 0. Now here I'm using the fact, which was observed in the previous lecture, that the convex hull of a circled set is circled. The convex hull of a circled set is circled, so this set is not only convex, but it is also circled. So it is absolutely convex. And it is a neighborhood of 0 because it is because it contains W, and it is contained in U, because W is contained in U and U is convex. And this completes the proof. As a corollary of this lemma, we obtain an equivalent definition of a locally convex space. Corollary. A topological vector space X is locally convex if and only if there exists base of absolutely convex neighborhoods of 0. In X, or equivalently a subbase of absolutely convex neighborhoods of 0. So just compare this with our original definition. Here we require the existence of a base of convex neighborhoods of 0. But we can always choose it, the space, we can choose a base consisting of absolutely convex neighborhoods of 0 by part 2 of the lemma. So first we construct a base of neighborhoods of 0 consisting of convex sets, and then we take any neighborhood from this base and replace it by a smaller neighborhood of 0, which is now absolutely convex. And we get such a base consisting of absolutely convex neighborhoods of 0. Okay, now by using the lemma, we can easily prove our theorem. Proof of theorem. So, of course, we have to prove only the left to right implication, because the left to right implication, the right to left implication is trivial. So we assume that X is locally convex, and we find a base consisting of absolutely convex neighborhoods of 0. Let beta be a base of absolutely convex neighborhoods of 0 in X. And let's construct a family of semi-norms out of beta, as follows. So the respective set consists of the Minkowski functionals of all sets V in beta. So by our previous proposition, each such function is a semi-norm because V is absolutely convex. So I claim that this is exactly the family we are looking for. Why is it so? So let's use this proposition. So by our previous proposition, we have the following double inclusion. The open unit ball relative to PV is contained in V and is contained in the respective closed unit ball. For convenience, we replace it with a bigger set, namely with the open ball of radius 2. So this follows from our previous proposition. And this double inclusion gives us the equality of the respective topologies. Well, indeed. The first inclusion, this one, implies that the identity map from X equipped with the topology tau p, with the topology generated by this family of seminorms, to X equipped with the original topology, the identity map, is continuous. Well, formally, this is the continuity at 0. That is, for every neighborhood of 0 here, V is a basic neighborhood of 0. We find neighborhood of 0 here, which is contained in V. So formally, this is the continuity at 0, but we have already observed at the previous lecture that a linear map between topological vector spaces is continuous if and only if it is continuous at 0. So it is continuous, and this means exactly that tau is contained in tau of p. And to prove the opposite inclusion, let's look at the second inclusion here. Formally, the standard subbase of neighborhoods of 0 for the topology tau of p consists of such open balls of an arbitrary positive radius. But we can easily replace 2 by an arbitrary epsilon as follows. So for every positive epsilon, we multiply everything by epsilon over 2, and we get the following inclusion. So this is obtained from this one if we multiply it by epsilon over 2. So well, this is a neighborhood of 0 from the standard subbase of tau of p, and this is a neighborhood of 0 in the topology tau. And this implies that the identity map from X with the topology tau to X with the topology tau of p is also continuous at 0, that is, it is continuous. And this means exactly that tau of p is contained in tau. So in summary, we see that the topologies are the same, and this completes the proof. So in summary, we see that that polynormable spaces, that polynormed spaces, are related to locally convex spaces in about the same way as metric spaces are related to metrizable topological spaces. So in other words, of course, the structure of a polynormed space is richer than the structure of the respective locally convex space, in the sense that, of course, the same topology can be given by many different families of seminorms. But in practice, it turns out that when we work with locally convex spaces, the concrete family of seminorms generating the topology is not so important. That is, what is really important is the topology given by this family. And because of this, the notion of polynormed space is not so much in use, while the notion of a locally convex space is absolutely standard and traditional. So I'll follow the tradition, and therefore I'll never use the notion of a polynormed space anymore. But at the same time, the fact that locally convex spaces are polynormable in this sense this fact is very useful, and we will constantly use it. Okay, our next goal is to give a useful continuity criterion for a linear operator between locally convex spaces. Continuity criterion for linear operators. So let's start with a motivation from the classical functional analysis. Now the following well-known fact, that if we have two normed spaces, x and y, two normed spaces, and the linear operator t from x to y, then it is well known that t is continuous even only if it is bounded, in the sense that there exists a non-negative constant c such that the norm of t of x is less than or equal to c times the norm of x. This is well known and standard. So what we are going to do is to generalize this criterion to linear operators between locally convex spaces. Okay, so first of all, let's introduce some terminology. Suppose that X is a vector space, and suppose we have two seminorms, P and Q, two seminorms on X. We say that Q is dominated by P, and write the following symbol, something like an order relation on the set of all seminorms. In fact, this is indeed an order relation. If there exists a constant C, and a negative constant C, such that Q of x is less than or equal to Cp of x for every x. So basically this means that Q is less than or equal to P up to a multiplicative constant. The Russian for dominated is мажорируется. So we say that Q is dominated by P, or that P dominates Q. The same definition can be given in more geometric terms. So we have the following proposition. First of all, Q is less than or equal to P, if and only if the open unit ball, UP, is contained in UQ. And for the domination relation, we have the following criterion. Q is dominated by P, if and only if the respective ball, UP, is observed by UQ. The proof is a simple exercise. Let's introduce some more notation. So we still have two seminorms P and Q on X. And we will sometimes consider the pointwise maximum, the maximum of P and Q. This is a function on X, which is defined to be the pointwise maximum. It takes every X to the maximum of P of X and Q of X. And it's very easy to show that the maximum of two seminorms is also a seminorm. This is also a seminorm. And the respective unit ball for this seminorm is nothing but the intersection of the open balls UP and UQ. This is almost trivial, so formally this is a simple exercise. Now, before we give a continuity criterion for a linear operator between locally convex spaces, we'll prove an auxiliary result, which nevertheless has an independent interest, and which gives us a continuity criterion for a seminorm on a topological vector space. Let's call it theorem 1. So suppose that X is a topological vector space, and Q is a seminorm on X. Then the following conditions are equivalent. Condition 1, Q is continuous. Condition 2, Q is continuous at 0. Condition 3, the respective ball, the open unit ball for Q, is open. I mean, open in the original topology on X. The open unit ball is open. And property 4, this ball is a neighborhood of 0. Let's recall that we adopted the convention, at the previous lecture, we adopted the convention that a neighborhood of a point is not necessarily open. So by definition, a neighborhood of a point in a topological space is a set for which this point is an interior point. In other words, there is a smaller open set containing this point. So these four properties are equivalent. And if we moreover assume that X is locally convex, over X is a locally convex space, and P is any defining family of semi-norms on X, then we have one more equivalent condition, that is conditions 1, 2, 3, and 4, are equivalent to the following condition 5. So the condition 5 is that Q is dominated by finitely many semi-norms from the family P. So it is dominated by maximum of finitely many semi-norms from the family P, for the sum P1 to Pn in P. Well, let's prove this result. So what is trivial here? First of all, let's observe that 1 trivially implies 3, because UQ is just the preimage of the half interval from 0 to 1, which is an open subset of the space of the positive half line. And 3 obviously implies 4. So if UQ is open, then it is obviously a neighborhood of 0. So this is clear. Now let's observe that 4 implies 2. So if UQ is a neighborhood of 0, then for every positive epsilon, we have the following inclusion. Q takes the respective bow multiplied by epsilon to the interval from 0 to epsilon, just by the definition of the set UQ and by the properties of a seminorm. And this is, of course, a neighborhood of 0, because UQ is a neighborhood of 0. And this inclusion readily implies that Q is continuous at 0. And finally, I will show that 2 implies 1. So we assume that Q is continuous at 0. It is very close to the statement that a linear operator is continuous if and only if it is continuous at 0, but not exactly, because Q is not linear, it is a semi-norm. But nevertheless, this is also very easy for the following reason. So since Q is continuous at 0, then for every positive epsilon, we can find a neighborhood of 0, say neighborhood U of 0, such that Q takes U to the interval from 0 to epsilon. Let's now take an element X in our space and observe then that if we shift U by X, we get a neighborhood of X. X plus U is a neighborhood of X. And for any element Y in this neighborhood, if we try to estimate the distance between Q of Y and Q of X, so first of all, by the triangle inequality, this is less than or equal to Q of Y minus X, because Q is a semi-norm. Y minus X belongs to U, and so because of this, this is less than epsilon. And this inequality readily implies that Q is continuous at X. So in summary, we see that properties 1, 2, 3, and 4 are equivalent for any topological vector space. And now we have to show that if X is locally convex, then all these properties are equivalent to property 5. So now we assume that X is locally convex and P is a defining family of semi-norms. will show that 4 is equivalent to 5. So property 4 means that UQ contains a suitable neighborhood from the standard base of the topology generated by P. So in other words, we can always find finitely many seminorms, P1, Pn, in our family, and the positive epsilon, such that this is equivalent to 4. So 4 is equivalent to the existence of such a finite n-tuple of seminorms and an epsilon, such that UQ contains the following basic open neighborhood of 0, corresponding to P1, Pn, and epsilon. So let's recall that this set is given by the following inequality. This is the set of all x such that Pi of x is less than epsilon for all I from 1 to n. This is a basic neighborhood of 0. This neighborhood can be written as follows. We can write it as UP epsilon, where P is just the maximum of the seminorms P1 to Pn. P is the maximum of this family of seminorms. Then we observe that this is nothing but the open unit ball, that is the ball of radius 1, corresponding to the seminorm, to this seminorm, P over epsilon, P divided by epsilon. So we see that property 4 is equivalent to the fact that there exists finitely many seminorms with this property such that UQ contains this ball. And now we look at this equivalence and deduce that this inclusion means precisely that Q is less than or equal to epsilon inverse P by the previous proposition. And this is exactly what we wanted to show. This is exactly our condition 5. So Q is dominated by the maximum of finitely many seminorms from P. So 4 and 5 are equivalent in a locally convex case. And this completes the proof. Here is a simple but useful corollary of this theorem. Corollary. Let X be a locally convex space. And before we state the corollary, let's introduce the respective notation. Let Sn of x denote the family of all continuous seminorms on X. All continuous seminorms on X. So we have the following corollary. If X is a locally convex space and P is a defining family on X, then all seminorms in P are continuous. That is, P is contained in Sn of x for every defining family of seminorms. Defining family P of seminorms on X. Well, why is it so? This is trivially true by property 5. Because if Q belongs to P, if Q belongs to P, then obviously it is dominated by itself. It is dominated by itself, so it is continuous by this criteria. So any seminorm from the defining family is continuous. And corollary 2 is that Sn of x, the set of all continuous seminorms, is the largest defining family of seminorms on X. The largest defining family of seminorms on X. Well, indeed, property 1 implies that Sn of x contains all defining families. And so the original topology on x, tau of p, is not stronger. It is weaker than the topology generated by Sn of x. But on the other hand, if we take a continuous seminorm on x, then of course the respective open unit ball is open. And so the topology generated by the semi is not stronger than the original topology. And as a result, these topologies are identical. So this family is defining. It defines the same topology. It defines the original topology on X. Okay, now we are ready to prove a continuity criterion for linear operators between locally convex spaces. This is our theorem 2. Theorem 2. Suppose we have two locally convex spaces, X and Y. The topology on X is generated by a family of seminorms P, and the topology on Y is generated by a family of seminorms Q. So they are two locally convex spaces, and T is a linear operator, a linear map from X to Y. Then the following conditions are equivalent. Condition 1, T is continuous. Condition 2, for every seminorm Q from the family Q, the composition of Q and T is continuous. And property 3, for every Q in Q, exists a non-negative constant C, and there exist finitely many seminorms P1 to Pn from the family P, such that for every X in X we have the following inequality: Q of T of X is less than or equal to C times the maximum of Pi of X. The maximum is taken over I from 1 to n. So we see that in the case of norm spaces, this property 3 is just states that just T is bounded. That is the norm of T of X. We have so the families P and Q consist of a single norm, and this means that the norm of T of X is less than or equal to C times the norm of X. So this criterion generalizes the well-known continuity criterion for a linear operator between norm spaces. And the proof is now very easy, modulo theorem 1. Namely, 1 implies 2. This is true by the previous corollary. So by previous corollary, every seminorm from Q is continuous on Y, because Q is continuous on Y. And of course, the composition of two continuous maps is continuous. 2 and 3 are equivalent by theorem 1. We simply apply our continuity criterion to Q composed with T. So clearly, the composition of a linear map and the seminorm is a seminorm. So this function, Q composed with T, is a seminorm on X. So we simply apply theorem 1 to the seminorm, and we get precisely the equivalence between 2 and 3. And finally, we show that 2 implies 1. 2 implies 1. Since this function, which is a seminorm, is continuous, we see that the respective unit ball is continuous. Is an open subset. Of X, and moreover neighborhood of 0. So this follows from the continuity. So U for every Q respective set, respective ball, is open in X. And let's now observe that this set is nothing but the pre-image of UQ under T. Just by definition, it consists of all X, elements X, such that Q of T of X is smaller than 1. That is, of those X for which T of X sits in UQ. So this is open. And this is almost the continuity of at 0, because such sets of the form UQ, if we multiply them by arbitrary positive numbers, we get a standard subbase of neighborhoods of 0. So, well, let's now multiply by an arbitrary positive number. So this implies that for every positive epsilon, the pre-image of the respective ball of radius epsilon, what can we say about this set? This is nothing but the unit ball multiplied by epsilon. And since T is linear, this is epsilon times T inverse of UQ. And of course, if we multiply an open set by a positive epsilon, we get an open set. So this set is open. And so T is continuous at 0. T is continuous at 0 because such sets form a subbase of neighborhoods of 0 in Y. So T is continuous at 0, so it is continuous. T is continuous. And this completes the proof. Well, let's now look at some simple examples of continuous operators between locally convex spaces. Example 1, or more exactly, example exercise 1. A linear differential operator on the space of smooth functions. So we take an open set U in Rn, and we define an operator T on the space of smooth functions as follows. So we take a family A alpha of smooth functions and form a finite sum of the following form. So alpha is a multi-index. The sum is finite, so we assume that the length of the respective multi-index is less than or equal to n for some n. And alpha are arbitrary smooth functions on U. So this is a linear differential operator. By using our continuity criterion, we can easily show that this operator is continuous. The exercise is to show that T is continuous. A similar example can be constructed in the setting of holomorphic functions. Example exercise 2. Now we assume that U is an open subset of the complex plane, and consider an operator T on the space of holomorphic function. So let's recall from the previous lecture that by script O of U, we denote the space of holomorphic functions on U, equipped with the topology of compact convergence. So the topology is induced from the space of continuous functions on U. And the operator is given by the following formula. So this is also a linear differential operator on the space of smooth functions. Here, AK are arbitrary holomorphic functions on U. Again, the exercise is to show that such an operator is continuous. And one more example, one more exercise. Is a little bit more advanced. Example exercise 3. Let's look at the space little s of z, which is very similar to the space little s introduced at the previous lecture. Little s consists of rapidly decreasing sequences. This space also consists of rapidly decreasing sequences, but now indexed by integers. So formally it consists of all sequences xn indexed by the integers, such that for every non-negative integer k, the following number, supremum of xn 1 plus the modulus of n to the power k. So such a number is finite. This is an obvious generalization of little s introduced at the previous lecture. This is a locally convex space with the topology generated by all seminorms of this form. Let's now denote by bold T the unit circle on the complex plane. Now let's consider the Fourier transform of smooth functions. The Fourier transform stripped f, it acts from C infinity of T, from smooth functions on the circle, to little s of z, to the space of rapidly decreasing sequences of complex numbers, and it acts by the following rule. It takes every function, every smooth function, little f, to the sequence of its Fourier coefficients, f of z to the power minus n, where we integrate with respect to the standard normalized length measure of the circle. When I say normalized, I mean that we divide it by 2 pi in such a way that the length of the circle, the measure of the circle, is 1. So the exercise is to show, first of all, that indeed f takes this space to this space. So show that f indeed takes smooth functions to rapidly decreasing sequences. This is basically a restatement of a standard result from real analysis, from the Fourier transform. And moreover, that f is a topological isomorphism. Topological isomorphism means a linear homeomorphism. A linear homeomorphism, that is a continuous linear map, which is bijective, and the inverse map is also continuous. A topological isomorphism between the space of smooth functions on the circle and the space of rapidly decreasing sequences on the integers. Может, конечно, но здесь это не критично. Тут можно честно проверить непрерывность в обе стороны вообще без проблем. Ну да, я про нее еще не рассказывал. Нет, здесь можно честно прям в лоб проверить, никаких проблем. В одну сторону и в другую непрерывность, вот прям по нашей теореме. So the idea is just to use our continuity criterion for a linear operator. So just to show that f and f inverse are continuous in a straightforward way. Okay, let's now come back to our continuity criterion for a linear operator, and let's now deduce some important corollaries. Some corollaries of theorem 2. First of all, let's look at a special case of our continuity criterion, which corresponds to linear functions, that is, two linear operators from a locally convex space to the base field. In this case, the continuity criterion looks as follows. So suppose that x is a locally convex space, and P is a defining family of seminorms X. And suppose little f is a linear functional on X. Then f is continuous if and only if the absolute value of f is a continuous seminorm of X. And this happens if and only if the absolute value of f is dominated by finitely many seminorms from our defining family. For some seminorms P1 to Pn in P. Well, this is just a special case of theorem 2. Now, by using this corollary, we can answer the question why locally convex spaces are better than general topological vector spaces. Well, actually, we have two advantages of locally convex spaces. We already know about one of them from the previous lecture. Namely, the advantage is that when we work with locally convex spaces, we have two equivalent languages, the language of seminorms and the language of neighborhoods of zero. And they're indeed equivalent in the sense that every statement which can be made by using the language of seminorms can be translated into an equivalent language of general topology of neighborhoods of zero and the other way around. But, well, this is indeed very useful. But on the other hand, this is the language of seminorms is something like a nice user interface for working with locally convex spaces. Probably a real advantage of locally convex spaces, if we compare them with arbitrary topological vector spaces, is that every Hausdorff we will shortly prove that every Hausdorff locally convex space has sufficiently many continuous linear functionals. And as a result, there is a very rich and powerful duality theory for locally convex spaces, which simply doesn't exist for general topological vector spaces. To prove this result, we have, first of all, the following corollary, corollary 2. Suppose that X is a locally convex space. X0 is a vector subspace of X. And we have the following extension result for linear functionals. So I claim that for every continuous linear functional F0 on X0, so X0 prime is the dual space, the space of all continuous linear functionals. There exists a continuous linear functional f on X which extends F0. So every continuous linear functional defined in a subspace can be extended to the whole of X. To prove this result, we take any defining family of seminorms on X, or maybe it is more convenient to take the family of all continuous seminorms P on X, all continuous seminorms. And let's observe that the topology on X0, the topology on the subspace X0, induced from X, is also determined by a family of seminorms. Induced from X is generated by the restrictions of the seminorms from this defining family to X0. Well, this is simply an observation which is immediate from the definition of the topology generated by a family of seminorms. So the intersections, if you take open bowls in X centered at points in X0, then the intersections with X0 are again open balls in X0. So this is kind of trivial. Okay, now F0 is continuous, is a continuous linear functional on X0, and we use corollary 1. By corollary 1, now corollary 1, there exists a seminorm P in our family, a continuous seminorm on X, such that F0, the absolute value of F0, is less than or equal to P on X0. Well, formally, in corollary 1, here we have a finite maximum and the domination relation, but clearly the maximum of finitely many continuous seminorm is also continuous, and if we multiply the seminorm by a constant, it is still continuous. So we have this inequality for a suitable continuous seminorm on X. So now we can simply apply the Hahn-Banach extension theorem. And basically, this completes the proof, because we have a linear functional on a subspace satisfying this inequality. We extend it to the whole of X such that the same inequality holds everywhere on X. But now corollary 1 means that the resulting extended functional is continuous. And this completes the proof. And now corollary 3. Suppose that X is Hausdorff. Is a Hausdorff locally convex space. Then, for every non-zero element in our space, we can always find a continuous linear functional f on x, such that f of x is not equal to 0. In other words, for every Hausdorff locally convex space, we have sufficiently many continuous linear functionals. Equivalently, this means that continuous linear functionals separate the points. The proof is very similar to the proof of the same result in the case of normed spaces. Namely, first of all, since X is Hausdorff, we can always find a continuous seminorm P on X such that P of little x, this is our vector, is strictly positive. This follows from the criterion which was discussed in the previous lecture. So if we take a polynormed space, then it is Hausdorff, if and only for every non-zero vector, there is a seminorm in our defining family, such that P of x is strictly positive. And now we define a linear functional, F0, on the one-dimensional space, subspace spanned by little x, by the following formula. It takes lambda x to lambda times P of x for every lambda. So clearly this is a linear functional defined on the one-dimensional space, and for every y in this one-dimensional space, the absolute value of f0 of y equals P of y. We simply choose lambda such that y equals lambda x. This implies that f0 is continuous by corollary 1. And now we apply corollary 2. Apply corollary 2, extend f0 to the whole space, and we get, and we obtain the functional f, the functional we are looking for. What is important here is that the assumption of local convexity cannot be dropped. If we drop this assumption, then the result fails. And there are many standard counterexamples. I'll give you only one of them. An example and an exercise at the same time. Let's consider, so we take an arbitrary measure space, x mu, a measure space that is a set together with a sigma algebra of subsets and a sigma additive measure. And let's consider the LP space, LP of x mu, which is well known to be a Banach space. But in our case, it is not a Banach space, because here we assume that P is less than 1. If P is greater than or equal to 1, then it is well known that this is a Banach space. But we assume that P is less than 1. In this case, we can introduce a metric, not a norm, but a metric on the space as follows. For every f in LP of x mu, we define the following number, which looks like something like a norm, but actually it is not a norm. It is just the integral over x of the absolute value of f to the power p. Не будем. Не будем. Не хотим. So here's an exercise. First of all, show that the following function of two variables, rho of fg, which is this quasi-norm, pseudo-norm, of f minus g is a metric. Is a metric on LP. So LP of x mu becomes a metrizable topological space. And moreover, it is a topological vector space. So this metric makes LP into a topological vector space. So it is a metrizable topological vector space. The ratios are continuous. If we now specialize to the case where x is an interval on the real line, and mu is the Lebesgue measure, mu is the Lebesgue measure, then it turns out that the topological dual of the space is trivial. The only continuous linear functional on the space is identically 0. So this example shows that corollary 3 fails in the case of arbitrary, that is not necessarily locally convex, Hausdorff topological vector spaces. Obviously, it is Hausdorff because it is a metric space. But it is not locally convex, and moreover, there are no linear functionals. The only continuous linear functional is identically 0. Actually, there are many other classical examples of the same kind. You'll find the details in the second exercise sheet. Which show that for general topological vector spaces, usually we don't have many continuous linear functionals. А я пока ничего особо не сказал, просто сказал, что она есть. Это мы этим еще займемся через некоторое время. Просто есть такая наука про двойственность для локальных пространств, довольно полезная. Но это потом. So the duality theory for locally convex spaces will be defined, will be discussed sometime in the second half of our course. Okay, so that's all for today. At the next lecture, we will discuss we'll discuss the useful notion of equivalence for families of seminorms. So two families of seminorms are equivalent if and only if they define the same topology. We'll deduce a useful equivalence criterion for such families, illustrated by some examples, and then we'll begin to discuss some standard constructions of locally convex spaces.